Welcome to the Comp 2503 Introduction to Trees video. This is not going to be a super long video because now we're just stepping into a new type of data structure after covering, the basics of lists, then learning about linked structures, then going into other things like stacks and recursion. And now we're getting into another form of linked structures, and why we spent so much time learning before is getting into trees. Then trees are a whole family of actual types of data structures, and so there's all different types of trees. They're all good for different types of problems. And so this video is just to bring up giving you a few examples of trees, get some basic terminology down before we step into specific types of trees in the course, then actually dealing with the implementation itself. So a tree is a non-linear structure in which the elements are organized into a hierarchy. So the idea here before is that when we were dealing with things like linked lists, that's a linear structure, that you have one element that connects to another, another. And so it's just creating one straight kind of line linear structure. Whereas now trees themselves are different, is that we'll still have nodes and things that connect things together, but what you connect afterwards will branch off like a tree, as you see like example in the imagery here, into different sides or different number of nodes depending upon the type of tree we're working with and the problem that it's being applied to. So a tree is comprised of a set of nodes in which the elements are stored and edges connect one node to another. So the idea is each node, just like a linked list, holds data. It will then have things that it connects to, and you have the edges being like this paths of who you connect to, and from one node to another. Now, visually getting to an example, there's stuff that you've already seen in your life that shows kind of a tree structure breakdown. Like here on the right is one that you're used to if we're visualizing, just files and directories themselves. That you may start in your home directory of your files and then have subdirectories that then have subdirectories from there or have specific subfiles. And you can visualize it as a tree-like structure where you have the top of it being a root, you have the actual other nodes that contain the data that then also keep branching down. So you can see from here that it is not a linear structure. It is not from one node to the next. It's from one to then sub ones that break off to sub further ones from this. And why it's generally called a tree is it's kind of like a tree, something that's flipped upside down. That you have the stalk root of the tree, then all the branches that come off from that down to what these endpoints here, which are going to be referred to as leaves, just as the names. So similar things like organizational charts for an actual company of what roles you have, like president to vice president, and breaking down is you have these different type of hierarchies and branching that happens from one node being connected to another. So now it's not just one node either connected to the previous, the one after in a linear structure. It is specifically, okay, well, I have one here that breaks down logically to other things. In case file systems, here are the files that are contained within this one. And then, okay, here for home, here's the one that's contained just within home, but not these other ones. And that sub-breakdown, or sub-breakdown of actual rules. So before going into some basic terminology that we'll need when working with trees in the future, I just wanted to give a few quick examples of trees, of like 1 to 3 examples of types of trees. So 1, expression trees. So a lot of times, say if this is a piece of code that needs to take a mathematical expression and execute it, or even if this is part of a program that has an equation that has to be executed, so you'd have your equation above, is you could represent this as a tree, as a possible way of taking this, representing it as a tree, as a data structure, and then writing an algorithm that traverses or works with that data structure as a way to solve this more complex problem. So in this case, an example of a binary tree, that means we have one node, but it branches down to 2 nodes below it at most. So it could be none, could only be 1, or it could be 2 that branches down from here each time, is that we have this hierarchy of what has to be executed, following the rules. Things like, oh, this C times by D's got to be done before you add B. So you see it down here. This work will get done, then it'll be combined with this work, then it'll be combined with work above, and then the final result of bringing everything together. So following orders of operations. It's a way to represent things. Another bigger example is parse trees, which you've dealt with without realizing you've dealt with it already. It's an ordered rooted tree that represents the syntactical structure of a string according to some formula or grammar. So one is your programs, all your programs that you're writing in Java and other languages. When it goes to actually compile it, it builds a parse tree, or a document object model, as it's called. So this represents the entire structure and execution and flow of the entire program before it goes on to compile and convert it when it needs to actually run it on the machine itself. So your programs, definitely if you've done the web course or dealt with that HTML, this is a huge way it breaks it down into a tree-like structure called the document object model, or things like XML documents. So example is a parse tree of HTML document. You can see on the left here a very, very basic hello world kind of HTML single page document. And where you're used to when you've worked with HTML is that you always have those opening and closing tags, and then everything is sub-contained in it. So your entire HTML document, you have the head, you then have the body, and tags that are defined between the opening or closing are considered to be inside the body. And in reality is that when a web browser is interpreting this, it builds what's called the document object model, which is a parse tree of the actual entire page. So you'll have one node starting at the root, which is your HTML, which breaks down to the children that are contained inside of it, which is the head, and then body references from here, and then so forth from there of all the tags that are embedded with each other inside of the body tag. So the body contains those two paragraph tags. And so a lot of times this is the way that the web browser will interpret it. If you're working with JavaScript, that's also ways that you can access and gain access to elements within that tree itself. Now, another one that's going to be more close to home in this course is binary search trees, which is going to be the main focus of your next assignment, is taking, going back to where you have a tree-like structure where it's more meant about the storage and retrieval of data, but done in a fast time. So I'm trying to be faster and following specific rules. So the idea here is this is going to be similar to the idea of a list that you had before, where you could store and retrieve information. So you can add to the list, you can search through it to find some information. But with a list, at the worst case, it could take n. If I'm searching for something, that thing I'm searching for could be at the end of the list. So the worst possible case is n. So as our complexity increases, asymptotic complexity, so the data increases from here, the complexity of the actual problem, well, then it's going to grow at a linear rate. Whereas here with binary search trees, as long as it's done properly and it's called what's balanced, we're hoping for that we can get an addition and actual retrieval of data in a log n, which is a much faster rate if done properly. And the idea here is that for, like, it's a binary tree, but all the nodes, so at any current node, all the nodes to the left of it will all be smaller, and all the nodes to the right of it will all be larger. And this allows for fast subdivision of the actual data. Now, I'm not going to go too deep into this yet because this is going to be future notes, so we'll go through more detail of how to add and remove and access and deal with information inside of a binary search tree. But I have given a link to a visualizer that we'll just step through. We can see some of the examples for now. So if I escape out of the notes, and let's go to the actual simulator. So there's a lot of different ones that are out there right here, and the idea of this is just starting. So we're going to get to different terminology at the end we'll come back to, but you have access to doing like what you expect with it, of adding, finding, deleting stuff from right here, getting the max, getting the min, and what does this actually take to build it. So we'll just start in the beginning, and this is like any other structure. We're dealing with data structure. We have one case where it's empty versus not empty, and when it's empty, it's just going to become the first node. So like linked lists, where we set it to being the start. In this case, the first node will be the actual root of it. So I'm just going to begin with the value 10, go insert, and you can see it pop in there. First node, that's the actual root. So next, when it goes to do an insert, this time I'm going to do 5, and the idea is it's always following the rules. If this is the node, when it comes to insert, it's going to compare from the root, and then it's going to keep moving till it can find an open location, and following the rules that it'll move to the left when it's smaller, and the right when it's greater, and then just stop if there's an actual match. So in this case, this is one node. It's going to check, okay, it's smaller. It's going to try to go to the right and see, hey, go to the left because it's smaller. So it's smaller, so it goes to the left. It's going to see that the left is open, and it's just going to add it to the left. Same thing if I went to do something that's larger, so I'll do 14. It's going to come here. 14 is larger than 10, so it's going to try to go to the right. It's going to see that the right is open, and so then it's going to actually put that into there. Boom. So this next pick a different one, say that where we go with 7. This is going to take a little bit more, is that the 7 is going to come in here. And it's going to say, okay, 7 is less than 10, so it's going to move to the left and see that left is taken, so it moves down to there. Then it checks again. Okay, we're comparing now 7 to the 5. Okay, well, 7 is greater, so it's going to move to the right. It's going to see that the right is open, and it's going to add it to that right. So first comparison, less. Next comparison, larger, and it's going to move it to the right. Same thing if I did something like 11. It's going to see greater, but then less than 14. Now, this may seem weird, like, why are we organizing the information this way? Is that, we could have just done it with the list and I had 1, 2, 3, 4, 5 nodes, but the difference now is going to come when I go to try searching for stuff. How many steps is it going to take for me to actually find something? So example, if this was a list and we were trying to search for something, the worst part, like the fastest case we could have is the first element, so order 1. The worst case we could have is at the very end of the list, so it would take 5 steps from this. So it's the worst case. Now with the binary search tree, the idea is that we move to the left or right, we are effectively almost trying to cut 1/2 of the data out so we don't have to search it. So each time we move to the left or right, we're hopefully getting where there's less nodes each time, if it's what's called balanced tree, and that we are seeing what we expect. So example, if we do a search to see if something's in there, and we're going to do an 11, it's going to compare, is this 11? No. Is this 11? No. Is this 11? Yes. And that only took 1, 2, 3 steps at worst to do that out of the 5 right now. So a little bit faster. And so as long as this is balanced, the idea is it's going to be halving this every time, and it's only going to take log n steps to actually find stuff. So let's do another insertion from right here. Let's do one where we do 3. So less than, move to the left. Let's do 4. Less than, greater than, -1. Should be less than, and we'll do 55. So you can start seeing the tree structure emerged. You can see even splitting the halfway at any node that we look to. If we go from 10, everything that's to the left of it is all values that are smaller than it, and everything that's to the right of it is always larger. So now the next step, if we had a problem of finding the maximum value in the entire tree, it becomes easier with this. If this was a list, we'd once again have to search through every element, and it's going to take n. Whereas if we know, okay, everything to the right of a node is going to be larger, so if we just keep going to the right, so we go to the right, keep going to the right, and just go all the way down to the right, we'll find, okay, 55 is the largest. Same for finding the minimum, is that you keep going to the left, because it'll always be the left of every node, and so if we go as far as we can go down left, well, we're going to have the smallest value we possibly could from right here, so that's -1. So this is more going to be useful for when we're doing storage and retrieval, and we're trying to do it faster where we have a lot of data that's coming in, and that we hope that we need to deal with all of this. Okay, so we're going to come back to that a lot more in the actual future. Now that was just one example, so the next set of notes we're going to go through is going to be a binary search tree itself. Here this was just giving you one example of one type of tree. So another example that you could have if we're doing like a binary search tree idea of just doing with names you can have ordered. But what this is showing is a problem that we have to keep in mind when we're working with binary search trees, is that the structure of the tree ends up being more defined by the order at which the data is coming in. And if the order comes in a slightly sorted order already, it's going to de-evolve into a linear structure from here. And so then it'll de-evolve from not being this branching structure and just go back to being like a linear structure, and we won't get any of the benefits of that searching and sorting. And that's why past binary search tree, there are all these examples of what's called balanced binary search trees. And so you get AVL trees or red-black trees that kind of handle that, okay, if the data is coming in sorted, it'll make sure to reorganize the tree so it always keeps it in a structure that's balanced for this fast storage and retrieval when we're going to larger, more complex problems. Another type of tree stepping into AI, and this is a very brute force kind of AI, is called the game tree. Now this is not good for every type of AI. It's generally good for two-player games where there is a limited number of options that each player can do. And that hoping that as you do more options in the future, the choices become less. So the example on the left is like tic-tac-toe. Other ones, potentially checkers from right here. I wouldn't really want to see a game tree for chess. It would grow really complex. But things like Connect 4 and other stuff, which would be an example we'll see later on, you'll see from here. Now, a game tree is a structure in the form of a tree consisting of the possible moves which allow you to move from a state of the game to the next state. And what it's used more for is that when it's the AI's turn to make a decision, the root or top thing you're dealing with is the current board, and then the next children that come down here is branching off is all the possible choices that AI could make. And then it looks at, okay, based upon each one of these choices, what are all the possible choices the other player could make? And then going down more level is, okay, after that, what are the possible choices I could make? And it's more like it's trying to look to the future and evaluate, based upon all combinations, what could be a good choice. So the further it can go and faster it can go down to looking at other levels, it can do better about making what can I do. So this isn't the playing the game as much as, okay, it's my turn, what are the choices and what could be my best possible choice to do by looking at my turn, then their turn, then my turn, and bringing back this evaluation. So I got an example here, and we will go through notes in the class, an example where you can play around with stuff of a game tree making its decision. So the example for this visualization that I was able to find here is just for tic-tac-toe, and with this version it's going to be hard to kind of beat the tree. And so we are the human player, and the other one, it's using what's called a min-max algorithm, which is an implementation of a game tree for its choices. And so right now it's trying to go to a depth of 2, so it does from the first level, it goes to their choice, then my choice, and their choice. So we'll start by I make my choice. So let's say I'm going to just go for the middle for X. And then it made its choice to move up here. The way it did it was then branching out. So if we go here, this is the entire tree that it built from 0, 1, 2. So depth of 2 going from here, okay, this is the beginning thing that it had. This is then the next choices that were then possible for what it could do. Right here. And then all the other possible choices that it could make from right here. And it did a ranking. So these bottom things that are called leaves will be all the future possible paths for the game based upon this, and then all the other choices that you're actually seeing. And then from there, it worked back from, okay, well, what was the best for here versus the worst for them, and picking a final ranking of where to go from there. So this is the tree. And so each time it's just trying to do, okay, well, you made the choice for the X here, and it's going to make the final choice here. Okay, well, what are all the choices it could then make past there? And so building up what it needs to versus future choices that it could actually make. So when I go to make another move here, let's say I try to do this one, then it's going to make its choices from, okay, this is the start, like the end state, to the next choices, from right here. Cases here aren't good, where you can see where it's doing a -10 of its evaluation. So a bigger part of this is going to be these evaluations that it does. As it comes down, it sees looks current board, what's the evaluation, and it's always trying to minimize and maximize. So I'm not going too far into this because it gets a little more complex and we need to talk about the algorithm. We'll do that in a future lecture. But the point is, this tree structure helps for, okay, what we start with, to other possible choices, and then their choices, and you have this overall tree-like structure which represents future possible states of the actual game, and this is where it could go based upon the choices you could have here. Now, we could go down deeper, which would take longer. So even if I do this, like update the tree, all possible choices that are from here, we can keep going. I'm like, hey, if I'm playing, I should probably block them. They're going to do this. But then it sees, oh no, this is an evaluation down here. This would be really bad to not, because they could actually win if they're going across this. Versus if I try to do anything and they do anything, and all the possible choices. So let me reset this again, and we can start with that depth of 4. If I start there, you can see that delay it took right here before generating this entire tree. Is that just look at all the possible choices and how huge this grows, just going down to a depth of 4 with a limited number of choices. But it's evaluating all of these to come back to what it thinks is the possible choice. So going down to here, evaluating this, and then propagating the value back up before it can go all the way, boom, to that original root, which is like way, way over here. Of like, okay, what can it do for its actual move? But getting better about the choices. So even if I try to like, okay, I'm going to do that. Okay, I need to block them. I have to block them. They still know to block me. But using this tree-like structure to get it so that the computer itself is looking to future possible choices, getting an evaluation of those future possible choices, and deciding upon which would be the best choice to make within the game itself. Okay, so again, we'll have more of that in the future. When we work on this, this is just a first introductory to that tool. So we'll be going through binary search trees, then we'll talk about game trees quickly so you can see a larger application of it from here. Now, before ending off these notes, I just want to get to some basic terminology. So this is kind of rudimentary, not as interesting, but we have to start building, okay, just like we had a starter head reference and end reference, and you had the next and previous and the terms nodes for linked structures, we now need to learn some basic terminology and tools that are then applied later on into other algorithms. So there's not as much context beyond, we need to know these tools before you use them, and they'll be coming up in the future actual like lectures on the binary search trees and the game trees. So trees concepts. Each node can have children nodes. A node with a children is called a parent. A node without a child is called a leaf. So if we look to here, we can see this top one, it has nodes that branch down going below it. Those are called the children of A, and A is the parent of all these ones below. Same thing here, like B is the parent of G, and A, you could think of the grandparent of it from right here, but G has no children below it, so it's referred to as a leaf node. A node can only have one parent, but may have multiple children. And that's just in trees. Graphs, this becomes different as a graph data structure. But here, for all trees, have a common thing that when I have a parent, every node that's here can only have one parent that goes above it. So you can see with all the rest of these are leaf nodes at the bottom. Their parent is F. The parent of F is B. The parent of B is A. And there's never two parents that come out of this. So it's not like a normal family genetic tree when we're talking about data structures. But then you can have multiple children that come below that. Where we get more specific, this is where we get to types of trees, then it refines saying how many children you can have within that tree itself. A node without a parent is called a root node, and there's only one root node in the entire tree. It is the starting point to access the entire tree, and all other nodes have one parent that are going above it. So this one node we see here at the top is the parent for B, C, D, and E, and this is your root node, and you can think of this being equivalent to your actual start node for the list. So we're still going to have things like moving references that move through this link structure, but the way that they will enter is they'll working with the root. We can also use this to tell if a tree is empty, because if the root is null, then the tree is empty and there's nothing that's contained inside of it. And so it's that beginning kind of connecting point between everything. And so now when I start saying the root, I am talking about that first node, which is the first parent that branches off to the other children that are then below it. Siblings are nodes that have the same parent. All siblings are considered to be on the same level. So when we talk about this as comparing the parent, if I know I have the same parent, we're on that same level. And levels start that the root is always 1, then all the children that go after that are 2, then 3, then 4 from there. A subtree is a tree rooted at a node below the root of the tree. So you can kind of have a branch that'll have a parent, and usually when we talk about a subtree, it's part of a larger tree, and just looking at one section where there is then one parent, including then all the children and sub-children down to leaves that then go below it. So for example, you have F, N, O, P is a subtree of the whole part right here, and then here D and all these nodes that are below it is a subtree of all these parts here. An edge is the connection between a parent and a child. So visualized here as the actual line, we refer to that as the edge now. And now a path is all nodes and edges between two given nodes. So to get to a point. So before, when we had a linear structure, there really was only the one path. It's from the first one connects to the next afterwards. But now here there's multiple different ways, like there's one specific way that we can get down to a certain point. So an example, if we were going between the path between P to A, you'd have A to B to F to P. So P, F, B, A is all in there, and then this edge, and this edge is all of the path from here down to here. A tree is balanced if all of its leaves of the tree are on the same level or within one level of each other. So the important from that is going off of being balanced. You can kind of see here is that if we split it in half, it seems to be roughly an equal amount, and we can see leaves are the ones that don't have any children. So all of these leaves, and they're all on the same kind of level, going from level 1, level 2 to level 3. Whereas this one, you can see, well, okay, this is leaves here, and this is like 1, 2, 3, 4, and so we have leaves on level 1, level 2, and level 3, and you can just even visualize it if we draw a line in between here and thinking of scales. This side seems to have more nodes than this other side, and this becomes important for some reasons. For some trees like binary search trees, being balanced is very important to keep up with that proper asymptotic complexity boost that we're expecting, that it's going to be faster to start searching for data. Now, two high-level classifications of trees that you can get is either you have general trees. So this means a node can have any number of children. So it can have 0 up to any number of children that come after this. So your things like your parse trees and that, let's say like HTML trees, that document object model, that would be referred to as a general tree. Or you have an n array tree where n is just representing some number being the specific number of children a node can have. So this means for an n-array tree, a node has a maximum of n children. So it can have from 0 up to that number. So e.g. a binary tree node has a max of 2. So this is a 2-array tree. So a binary tree has a maximum of 2 nodes per children. Other tools you can start having is things like the depth of a node. So how far down from the top the node is. So the root is at 0. And the path length from the root of the tree measured by the number of edges in that path. And so remember the path is the edges and the nodes from one node to another one. And the depth, when you think of this, is more like, okay, if we're going from the top and you're going down to a node, how far away from the actual root or one specific node is this? So if we did the depth, you can expect, okay, from the root to other nodes, you have it where it's 0 for the root, and then this is 1 step away from the root versus 2 steps versus 3. And you can see this 1 edge, 2 edge, 3 edges to get down to here. Now where the depth becomes important is some algorithms, they're say dealing with things like AVL trees, which is a balanced binary search tree, is that the algorithm needs to know the depth of a node and be able to calculate that to start detecting, is things getting out, like what's happening, are things are unbalanced. So is there one node, are there more nodes on one side, the left or the right, that have a deeper depth or are hanging down further? The height of the node is kind of the opposite, is how far up from the bottom. So leaf, height of itself. The longest path length from that node to the leaf is the subtree measured by the number of nodes within it. And so this is more from right here, starting at the leaves, it's 1, and then going up from here. So from this leaf to this one, and comparing from both of these. So here, from this leaf here, there's 1 edge, here there's 1 edge, and so, okay, this is that longest path going all the way up. Whereas for this one is, there is nothing to the left, but it goes down, okay, well, here's 1, from here is the 1, 2, so the leaf so 1 to 3, versus this other side where we get 3 is 1, 2, 3. So 1, 2, 3 for the actual nodes, versus right here it's the 1, 2. This is the longest chain. So these are kind of weird to bring up things at height or depth, but it's more for different algorithms that we'll potentially see in the future. Now the level of the node is the 1 plus the length of path from the root to that actual node. So root is always considered level 1. So you guys see this is 1, then to 2, then to 3, then to 4. Now, finally, and these are important that you'll just have to remember that from here, is that we need to do traversals of trees once in a while. And really what this is, it means visiting all the nodes within a structure once. So you've done this before, like when you're doing linked lists or just doing arrays, it's just doing a loop and stepping from one node to the next to the next. But from these basic linear structures that you've dealt with before, you realize, well, it's only from one to the next. So to visit, you just linearly step up one step to the next to the next. And so it's normal. But for nonlinear structures like a tree, the possibilities are more interesting for how you can start going through and how you visit them, as long as you visit each node once. But the order in which you visit them can have a different way that you process the information within that actual structure itself, depending on the type of tree that you're working with. So traversals is, when you hear this, is tools for these nonlinear structures that must visit / push each node exactly once, kind of like looping through. But then you get different types of things like pre-order and in-order, which visit the root, then traverse to the subtrees of left or right. So they'll visit them, but which order does it start going through? So things like pre-order, in-order, post-order, and level order. Now, I'm not going to go too in-depth to these because what they are is generally a recursive algorithm that you will see is that it starts stepping through the nodes and why we needed recursion. And the idea is that all the traversals will do the exact same thing, that they'll visit every node in the actual tree once, applying and doing what work you expect for it there. But it's which order does it go first? Does it go to the bottom and go the way up? Does it go from left to right? Does it go from top down and then keep going over? And depending upon the problem you're working on, then maybe a different traversal has to be done depending on what order you're dealing with stuff. So example, like game trees, you want to go to the bottom and traverse coming back up, versus other formats you're dealing with, like the top where we're trying to find the location and travel through it. But in the end, if we just need to go through every node once, even just to print them out, then any traversal is useful for this. So these slides quickly show the algorithm, the idea of the pre-order, that you're doing the action first and then visiting the children, and this does it recursively from right here, versus the in order, which is for all the children to the left, then doing a visit, then all the children to the right, or post order, which is visit all the children first. So go through all the children first, recursing on them, and then visit them. This is all different right here, but just be aware that they're all the same in the sense of, okay, I need to visit each node once, and it's just going to be a tool for which order I need to do. If you don't care about the order, you can use any traversal you actually want to itself, which is any one of these actual algorithms, or you need to do a specific one when working on that. So this, I'm not going to go too far into these right now until we're dealing with more specific trees, because you have to have a context of the type of tree and the data you're working with to make more sense of which traversals are best to use and how they work differently. So that's why I have coming up next the binary search tree kind of stuff, and then the game trees, and showing, okay, well, different things we can use there. So from there, I'm going to stop. This is our first basic introduction to trees, and the next things when we get into binary search trees, we'll step a little bit deeper and give more context into one specific type of tree and how to build it and then how to use it. Other than that, I hope you all continue being the awesome people I know that you are.